Welcome everyone. There are some familiar faces that I've seen here, and it's been a while since we've done a session, so really good to see you. For those that don't know me, my name is Dylan. I'm the co-founder of Digitalent. Outside of helping companies scale their AI products and engineering teams, our biggest focus has been fostering and building communities, which we think is really important in the AI space. Advancements are only accelerating hugely in the AI space. Just this month, we've had new flagship releases from Anthropic, OpenAI, Google, XAI, plus a fresh wave of kind of huge open weight models out of China, which has all been quite exciting. With these sessions, we've wanted to create an environment, I guess, where people can connect and learn. And I feel like we've brought together some really great people over the last few years or so. So it's been a pleasure to host these sessions with Mike. On to Mike. Mike's one of our community members. He's the brains behind these sessions. We'd be nowhere without him. He's an expert in the AI space, a great presenter, and yeah, someone you can always rely on for advice and support. So yeah, we're really lucky to have him. Mike's going to present for about 50 minutes or so, and that'll give you all 10 minutes or so at the end to ask questions and engage where need to be. Mike, I'm going to leave it to you, mate. I know lots happened.
No, thank you, Dylan. Appreciate it. Your introduction is always so nice. I need to turn down like the red color on my webcam, because otherwise I'm just continuously turning red. Thank you very much. Awesome. Hello, everyone. For those who do not know me by way of introductions, some I see the returning people. So Paula, good to see you again. Also, hello to Karim. Obviously, we said hi to Rom already. Gokul, good to see you all. Thank you very much for joining. Especially during this, time of the year, middle of the year tends to be sort of like the busiest time of the year. So we really appreciate you making the time. But also at the same time, I can promise you that this one will not disappoint. We have some fantastic papers lined up for you, and some of them are a little bit mind-boggling, especially the last one, so stick around for that. So, by way of introductions, my name is Mike. I'm a product leader, I'm a CPO, and a technical product manager. I've been an AI and ML enthusiast for quite a while, since approximately 2008, and I've had the opportunity to maintain that passion throughout my work. At the moment, I do manage product and engineering teams that are focusing specifically on delivering AI and machine learning value propositions, as well as helping some companies with their AI and AI-first journeys. Now, that requires me to obviously stay very close to the space and follow the space very closely. And that makes it easy for me to present on the latest developments in AI, which is what we're going to cover today. Now, as a disclaimer, and some of you who are returning will know this, right? If you are an AI researcher or an AI engineer yourself, right, you're working in this space, there is a chance that you may have heard about some of the things that we're going to talk about today. You might not have heard about them in that sequence or in that context, which could still be valuable, because I tend to frame these paradigm shifting developments in the context of particular themes and trends. But you might be aware generally about the general developments in that space, because obviously it's your job, right? If you are not, right, do not dismay. What we're going to do today is to take what I believe are the most prevalent paradigm shifts that we've seen in the AI research space over the last 30 days alone. So everything is very fresh. And what we do is we weave a story around this that lets us put all of this into perspective and specifically help us product people, but also technical people, engineering stakeholders, right, get a feel for where the AI space and the technology is heading in general, right? From that framework, however, you can probably tell that what I'm not going to do is I'm not going to include every piece of AI news or research out there over the last 30 days. You can probably tell way too much out there, right? But I think throughout this presentation, we're going to dive into a few papers that will help us put some of the key innovation points into context and give everyone something really tangible to walk away with, whether that is something that you apply technically or something that you use in your conversations around where AI is going and how you need to shift strategically in order to accommodate those changes. Now, as always, what we usually tend to do is start with a little bit of levity, right? So it's a tradition, right? We usually start with something reasonably funny or light, right? And I think this is a little bit hilarious because any person that is working in an engineering capacity knows immediately what I'm talking about when we're watching this video, software engineers before AI or after. And the difference, of course, is that you cannot get your laptop to sleep because Claude is always working away in the background processing the latest prompt, and you do not want to interrupt that, hence why you're walking around with an open laptop. I've seen that happening at the various companies. I've done it myself, right? And is also a really good segue, right? Because the papers that we're going to talk about are specifically defined as a paradigm shift because they fundamentally change how we build, architect, and even think about working with AI agents, right? We're now at a place where this is becoming a day-to-day occurrence, even for engineers who have been able to resist the trend for a reasonable amount of time, right? The technology has infiltrated every corner of the engineering and product space, and rightfully so, because it is a really interesting a way to enhance productivity and up-level engineers to become absolute weapons because they already have fantastic knowledge that they can apply this technology in the context of, right? Now, the journey that we're going to go on today is, in the first paper, we're going to present an architectural challenge most of us don't think about when building these AI agents or working with agent clusters, which is what happens when an AI never forgets, right? Specifically, we're talking about memory management. We're going to talk about a couple of techniques or a framework that has been proposed in order to make that a much more valuable proposition and avoid issues when you're building systems at scale. The second paper presents a new way or a new standard in the way agents will communicate to each other in the future. Spoiler, they will not just abandon English, but they will abandon talking entirely and start communicating brain to brain. So that will significantly impact how we're building agents, probably here in the next 6 months or so. And then the final paper, and that's the paper that we're going to spend the most time on, which is probably yet the strangest, but also probably the most important paper we've ever covered, is a paper by Anthropic, where Anthropic is openly asking the question whether Claude is conscious. And also, spoiler warning, the answer isn't a definitely not, which is interesting coming from a really, really large company like that. But the upside is, right, by looking under the hood of all for all of those research papers, we tend to find a new way to intervene when these models are operating across interaction vectors that are maybe undesirable. It allows us to make sure that when we're working with those models, we get to implement new evaluation mechanisms, right, and allows us to become way more efficient when we're building those systems. So we're starting with the first paper, which is called Always on Agents, a survey of persistent memory state and governance in LLMs. And it's an interesting paper because it is a survey that looks at persistent memory state and governance in LLM agents. And to understand why this matters, we need to understand the difference between the AI we have been using, right, and the AI that is coming. So some of you who might be returning may be recognizing this graphic. This was our treatment about 4 or 5 months ago when we talked about OpenClaw for the first time, right, ephemeral, stateless agents, right, where we are essentially building the agents around episodic context that goes away after your prompt has essentially been processed. So the agent spins up, right? It gets some context from its conversation history. Maybe it ingests some ND files as skills, generates and outputs right back to the conversation history, and essentially dies. And that is intentionally done so because long-term memory causes a number of problems, right? They receive tasks, they complete it, and then they reset completely, right? The downside is they wake up with complete amnesia on every single prompt. Now, this has downsides right? But the upside is that safety in that context is actually quite simple, because the agent cannot carry any mistakes forward between the different episodic interactions that it has. Always on agents, however, are a little bit different. And this is the paradigm that the research community is driving towards currently very aggressively. Its defining trait is that not that it runs around the clock. Claude agents, like Claude agents, for example, or agents that are similarly built can do that as well. Its defining trait is that it maintains persistent state, which means any future behavior that it engages in depends on every single memory that it had accumulated across the thousands of early interactions with you or your business or your customers and clients, right? Now, this study that was conducted, right, is not a small study. They analyzed 435 different works just to map out the current landscape of how AI memory is being treated. And when I say memory, what I mean is, I don't just mean whether it remembers your hometown or your name, or whether you prefer dark mode versus light mode, right? The paper focuses on a thing called control relevant state. So it looks at, you may have seen this before. There are sometimes task ledgers that track any open commitments from the LLM. Sometimes you give it a task, it says, okay, first I do this, then I do that, then I do this, then I do that. It tracks those things. It tracks permission states. So that dictates what an agent is authorized to do on your behalf, and trigger conditions. And trigger conditions are sort of like the rules that the AI writes for itself about when it should proactively act without you asking to act first, right? So those tend to be things like, oh, I'm going to write to a file, or especially if you're engaged in writing loops, right? You're essentially defining trigger states where the agent continues to go around in a loop and work on a task until it reaches a goal state, at which point it is allowed to stop. Right. Now, you might ask, how is this different from just giving the LLM, context windows or little instructions or conversations histories, the way we've done it in the past, right? The difference is that in these kind of episodic systems, right, the LLMs usually consume what they are fed. You provide a document, the AI reads that document, and then afterwards it dies, it drops the state. It doesn't remember, right, what you asked it in your previous interaction, the previous question that you asked it. Always on agents are a little bit different because they write and they continuously mutate their own state. They're actively curating their own brains. And the problem that comes with that is that if the agent writes itself a bad rule once, it owns that rule forever. And the question this paper asked is, how do we manage this dynamic, right? And how do we ensure that when we're accumulating all of those memories in those agentic systems, that they are accumulated in an auditable format that makes sure that bad memories go away and good memories are brought to the surface when they're needed. And what this paper points out is that when we're building agentic systems, usually we have this obsession, which is a forward arc obsession, right? Essentially, the field is currently focused on managing memory just by observing it, writing it, and retrieving data. That's all that is. But what we are completely forgetting about is the return arc, a mechanism to govern that data once it's stored and to delete data and or memories that are not required anymore. That's almost completely ignored 100% of the time, right? Now, the most that current agentic systems and frameworks are implementing are things like understanding when a certain memory deserves to be rolled back. But at the moment, there are zero mechanisms to undo a mistake that has been saved in memory. So in effect, what the industry is currently building across all of those 435 works are massive digital hoarders, right? We are creating AI agents that are hoarding and hoarding and hoarding and hoarding memory. They continue writing it, right? They might continue summarizing it, right? But what we're not doing is we don't implement trash can features, we don't have return policies, and we have no idea where half of the memories that get written to an AI agentic system either comes from, where its provenance comes from, and or whether it is still relevant. And when the researchers looked at this problem, they identified these 6 axes that should really matter when it comes to managing AI memory, right? And that is memories that refer to authority. So any licenses that the system believes it was granted in order to share, to shape further behavior, right? Essentially asking the question, well, who do you think permitted you to influence this next action, right? You might think of it like giving your agent permission. Maybe you have an agent that you use to book travel, right? And you say, look, please book this particular cheap domestic flight for me today. And it manages to do so. It has a successful interaction with the travel portal. You get your flight, all is hunky-dory. You giving that agent the authority to do that today, does that memory give the agent the authority to book the same the same flight, right, in December for 3 times the price? Obviously not. But the way most current systems are built is that they treat every stored memory equally, and they feel equally entitled to trigger actions forever, and they completely ignore the decay of user consent, for instance. So authority is a huge, huge problem. Similar to provenance, right? Which is knowing where a memory comes from. When provenance is missing, you get a failure mode with a wonderfully shady name, which is corroboration laundering, right? Which refers to an instance where an agent might ingest an untrusted source of information. Maybe that's a phishing email, for instance. And even if that phishing email was identified as being, a threat and should therefore not be taken seriously, if an AI agent was to ingest that, one of the first things it's going to do is to summarize it. And when it does so, there is a very high chance that it drops the source metadata and that it strips off the warning label that said that this came from a sketchy source, right? A month later, the agent is running a financially risky task, right? Pulls up that fact, and because the metadata is gone, it treats the poisoned external claim as an unshakable internal truth, because it literally laundered that external noise into a fact. And because it has no return arc, there's no way to trace it back where that fact came from. So these are some of the problems that memory systems that are currently being deployed in large enterprises. One client I'm working with that is also building a memory system. Those are very concrete problems that we need to specifically build an architect for in order to prevent these kind of interactions, right? Some of you may hear the expression second brains that are currently being thrown around in a lot of enterprises right now, right? Where the idea is that your company, if they only have an enterprise-wide shared memory, you can have agents dropping in and out of that memory constantly in order to make everything around you more effective, right? Those kinds of problems that we're seeing here are the kinds of problems that will cause very concrete pain if memory management isn't taken seriously in the architecture of those systems, right? Now, why does this matter? It matters because there is a thing at play with agents that is called the plasticity stability trade-off. It's actually a concept that's borrowed from neuroscience. And that trade-off suggests that every time the agent learns a shortcut, right, it gains plasticity, right? It adapts every time it gets a new skill, right? But without the ability to cleanly forget or roll back, right, it also accumulates entropy, so chaos, right, disorder, and it accumulates that disorder at a much faster rate than it expands its capacity to deal with that disorder. So stale facts, biased skills, expired permissions, they can create a massive problem. And eventually the agent will be required to dig through a junk drawer of its own making every time you ask it something, right? The obvious question is, why has nobody added a delete button, right, to those memories? Right? Wouldn't it be really helpful if you could just say, look, that permission that I gave you 3 months ago, just auto delete that, right? I don't even need to know about it, right? If you need to seek permission to buy something, if I hadn't given you permission within the last 3 months, please don't use my credit card. The problem is that the substrate, so the physical places where the memories inside of these agentic systems lives, they're actually really hostile to governance, right? Memory in agentic systems, yes, on the surface, they're managed in, markdown files and things like that for those who are working with them, right? But under the hood, what you have is a thing that's called a parametric memory, right? Which means that the AI learns and remembers by updating its own model weights. And from a governance perspective, this tends to be a total nightmare because it has what researchers call a no-native tombstone. A memory is essentially a path that exists in the neural network that the LLM built for itself when it was trained. And because it's a path, you cannot point to where that memory died, right? Where you deleted it, because you cannot reliably point to even where that memory lived in the first place. That memory is smeared across billions of mathematical weights that make up the model itself, right? So it's really, really difficult to go in and delete a particular fact, right, that you previously introduced to an agent in a previous run. The second one is context windows, right? These tend to be ephemeral, right? They tend to clear when the session is done, and therefore obviously not really suitable to govern long-term state or long-term memory. And finally, of course, we have vector stores, right? And their fatal flaw is that they have a property that's called mutation blindness. So it's a fancy term for essentially saying they have no temporal dimension, right? An LLM doesn't know when it was created, when a memory was created, right? It doesn't know who authorized that memory or what an older memory was supposed to be replaced by a new memory by, right? Essentially, it's like writing in permanent marker on a giant whiteboard, right? If you have a new fact, you write it next to the old one, and you're just praying that the next time you ask the LLM something about that memory, it will grab the new one rather than the old one. But the LLM, in essence, won't be able to distinguish between the two, right? So the obvious solution for this is version control for memory, right? To understand when edits were made, right? Being able to roll back, being able to delete some of those edits, hitting undo if need be. And this is exactly what this paper suggests. Now, I do realize that this is a really ugly slide, but I decided to keep it that way for those of us who are building those systems, because it can serve as a really nice checklist for you to consider when building particularly enterprise-grade agentic systems that are really heavily memory reliant and need to solve problems on really long interaction horizons, right? This particular framework comes from an evaluation mechanism that's called the always-on evaluation protocol, that this paper introduces, right? Where the researchers decided to not just score LLM agents on intelligence, but on their ability to govern their own memory. And this framework called AOEP, it's technically an evaluation protocol, but its real value is something else. It sketches the outline of a proposed state machine design for agent memory, right? State machine is a machine that essentially understands which memories are currently current versus ones that are outdated, right? It understands which ones are ready to be used and in which context, right? And that design goes a little bit like as follows. You should design, according to those researchers, your agent to only allow that agent a limited amount of memory operations, specifically 11. That is read, write, update, delete, right? We're all familiar with those, right? But also make sure that every time you delete something, you add a tombstone entry to a deletion ledger that makes sure that you can look through that dedicated ledger and determine exactly which memories were deleted and which sources they were deleted from, to make sure that all of the memory was deleted and nothing was residual, right? You have something that allows your agent to share memory. So that extends a record scope to maybe another user, another agent, or a group, right? Unshare revokes that, right? Validating checks a record before it becomes durable or authoritative. Ability to quarantine certain memories, right? Denying their right to the memory bank and or rollback. And you can see, right, that is a level of complexity in the agentic design that we usually, right, do not even consider when it comes to building those kinds of systems, right? And so the paradigm shift that I'm pointing out here is, at the moment, I'm aware of particularly 2 companies in the US who I'm working with, who are taking this paper and these requirements to build their own agentic state machines. Over the next 6 to 12 months, I think we're going to see frameworks popping up left, right, and center that are also going to use this particular framework, right, in order to make sure that memory and its provenance will play a much more important role in the way we're building those systems, right? So that is paradigm shift 1. Paradigm shift 2 is talking about how that memory is used in agentic interactions. Because our second paper is honestly, it's a little bit wild, right? When it comes to agents, usually we're building those agents with with a number of roles. For example, this is a pattern that we are very familiar with. This is the planner. There's the critiquer and the solver, right? The planner tends to draft the approach. The next one finds logical flaws, and the solver finally, delivers the right answer. What the researchers have found in those agentic interactions is that one of the bottlenecks tends to be the medium of exchange. And this also tended to be emergent behavior. If you look at something like Claude, for example, right, it doesn't take agents that are sort of let loose in an uncontrolled environment long to start inventing their own language, because English is just so inefficient. But this talks about something a little bit different, right? It still has the same problem, right? In the sense that when you use agents in a collaborative setup, each agent is required to finish their calculation. That's usually happening in pure math, translate all of that internal mathematical processing into plain English, and then it is required to pick the next text token, essentially one by one, right, before it can share that output with either yourself and the next agent, right? And then what happens is the critic is then required to read that paragraph, re-encode it back into its own internal mathematical interpretation, and then encode it to yet another English paragraph. And every one of those translation steps, right, that takes compute, that takes latency, it takes tokens that you're quite frankly, paying probably too much money for already, right? Because we are required to wait for a machine to type. That is obviously one set of problems. The other set of problems is that there is a more fundamental issue with working on human language when it comes to agents. And that is called the vanishing gradient problem. Because here's the thing, right? When you train an AI system, the learning signal, that's called the gradient, right? It flows through the network. So it flows forward. It also flows backward to correct errors. And that requires a smooth, continuous mathematical path. What that means is that to an LLM or a model, right, nothing is ever black and white, right? Everything is a probability, right? Might be, you know, a 30% chance of being white or a 70% chance of being black, right? And then you come up with, I don't know, maybe gray, right? English words, however, they're not continuous. They're entirely discrete. So when a model outputs a word, let's say cat, or the word dog, it's not, oh, this, you know, animal is 30% dog and 70% cat, and therefore we call it cat. No, there's no smooth curves between those things, right? When a LLM learning signal hits text, it's required to hit a brick wall, and the gradient vanishes entirely. But that level of nuance is really detrimental to the performance of LLM agents working with each other and collaborating as a team, right? That mathematical nuance, that continuous position on a continuous curve is really, really important to those LLMs when they wish to communicate with each other. But we are essentially forcing them into a black and white box, and therefore it requires them more effort, more compute, more tokens, and a loss of a gradient nuance that ultimately affect their output and how well they can perform. So what the researchers did is they went ahead and did something a little bit radical, which is they went ahead and went into removing the human language entirely, right? So instead of requiring these agents to decode their conclusions into English before they're sharing them with each other, right? The agents went ahead and were enabled to pass their latent thoughts. So that is the raw, unencoded, high-dimensional matrices, right? The math stuff that's happening under the hood, right? The thing that actually represents the model's actual internal processing to each other, right? First agent finishes its computation, and rather than translating it into English, it just hands its raw neural embeddings, right? Like a matrix of numbers directly to the next agent, right? And the text step completely bypassed. Now, if you have a little bit of an inkling into how models are working, you'll probably spotted a little bit of an issue here, which is often you give a planner model a more powerful model, right? You might have a 10 billion parameter model that you make the planner, and then a smaller, maybe 1.5 billion parameter model might be the critic, right? Those models, they can have totally different architectures. So the question is, you know, how do you make them share mathematical representations when those might look very different under the hood? And this is actually where this paper's innovation comes from, right? Because while this might sound a little bit like plugging a USB drive into a toaster, the solution that these researchers came up with is a really lightweight 2-layer projection module that they put in between, that they append to existing modules that can act as a bridge, and that comes in 2 flavors, right? There's the inner link here, which essentially handles an agent's inner monologue. So when an agent talks, when an agent works on a problem, it might run through several cycles of inner monologue. You would be familiar with that cycle obviously being output into a chain of thought. You know, in the past you were able to read that chain of thought, with some of the ChatGPTs and Anthropic. You can still do so, right? And it continues cycling through that until it feels it is done, right? This inner link just maps the agent's final layer straight back into its own output, and it creates sort of like a closed loop that runs continuously through so that the agent can chew on the problem without ever having to write a chain of thought down, right? Saves tokens, saves latency. Great for the user, right? The outer link is a universal translator that was designed for different LLM models to talk to each other. So agent 1 talking to agent 2. Sort of like universal translator, it takes the raw hidden representations of one agent and bridges them into a completely different mathematical space for the next. And what that does is, if you hook up agents that way, it changes the entire shape of the collaboration. So with text, right, you essentially had a linear assembly line. Agent 1 created its outputs, agent 2 took it, created its outputs, sent it to agent 3, and unless you deliberately programmed a feedback loop back, right, that output was the final thing, take it or leave it, right? With this link that these researchers built, the system of agents, right, which we perceive as inherently separate because we programmed them separately, right? They become one single unified loop, right? Agent 3 feeds its latent output back to agent 1, and they continue to refine the solution as one sort of like amorphous blob of mathematical interaction, round after round, entirely in silence, and only the very last agent turn after the final round tends to switch to the text decoder and writes an answer for the human. It's a little bit like a team of writers sitting in a writer's room, doing all the messy drafts in their head and only printing one polished copy for a producer to read. And because this entire loop now is continuous math, right, the learning signals that are being exchanged, they can flow back and forth through every agent and every round, and you're no longer required to train 3 employees who occasionally email each other. It's more like working with one single hive mind whose synergy is sort of like baked into the weights, which is really, really cool. Now, the question is, why would anyone do this, right? Is this even effective? And the answer is absolutely. So across 9 benchmarks, the last 2 rows are probably the most important ones. AIM 2025, this is the American Invitational Math event or exhibition. I can't remember what it is. It's a big math competition, right? One of the most quoted benchmarks that you have, all the large LLMs go up against, right? We see a 8.3% improvement. But that improvement and those results are based on sub 10 billion parameter models. You can run with the right architecture and the right laptop, a 15 billion parameter model on your laptop. Sub 10 billion parameter is really small. We're talking about Gwen, we're talking about Llama, right? These are really cheap models that suddenly perform at a level comparable to something like Opus 4.2, for example. Really, really powerful, right? Not, not Fable just yet, but in striking distance. Now, not only do they perform much better, they also perform much faster, and they reduce their tokens quite significantly because the intermediate reasoning steps tend to evaporate into the latent space, right? And it is for that reason that researchers and the research community is currently thinking that this will become the standard way that agentic clusters will continue to interact with each other moving forward. So over the next 3 to 6 months, expect that there are frameworks that are coming out that will allow, and connectors that are coming out that will allow that kind of agentic interactions between models. Now, obviously, this is good for any company's wallet, right? Cheaper models, performing better with way less tokens. But obviously, there's also a little bit of a question that should make us slightly uncomfortable, right? If agents tend to abandon human language, right, there's no paper trail anymore, right? When there's a medical diagnosis or a financial agent swarm moves a market, right, we cannot read their reasoning because those intermediate steps were deliberately evaporated in the latent space for the benefits of speed and cost, right? The upside is, of course, we're getting significant computational power, right? But we are sacrificing the very transparency we need to trust those systems. Now, the good news is there may be a new way to look under the hood of how these systems work in order to introduce accountability regardless. And this is the last paper that we're talking about, and this is the big one. And I want to slow down for this one because I want to give it the time that it deserves. Now, this last paper, which Anthropic just published a week and a half ago, essentially, is probably one of the most strangest and probably one of the most important papers that we've talked about in these sessions. It is strange and important for one particular reason. The research community agrees with that reason, and that is that Anthropic goes to great length to not say that Claude is conscious. What they do, however, say is that Claude has a kind of consciousness. This is in the paper. You can read this yourself. This is not interpretation. These are word for word, verbatim quotes, right? And we'll talk through what that means, of course, right? It is also for that exact reason that this paper went, of course, absolutely viral. Probably not as viral as it could have been, probably because of the World Cup, but in the research community, it just absolutely shattered records, right? Because what the team at Anthropic discovered was, and this may sound anticlimactic, but I'll put this into perspective here in a second, is that Claude has a small internal workspace where its thoughts are understandable, they're controllable, and where they affect the final output. And to illustrate what I mean, I'm going to read you a quick quote from that paper. And that quote goes as follows. It starts with, of everything that's happening in your brain right now, only a tiny fraction is consciously accessible. Thoughts you can describe, hold in your mind, and reason with. We found a strikingly similar divide inside of our Claude model. And to understand what that actually means or what they actually discovered, there's one concept that I quickly want to bring up. And I bring it up because the paper brings it up itself. And that is called the global workspace theory. It comes from neuroscience, right? Like biological neuroscience, where scientists call it the global neural workspace. And the idea tends to be reasonably simple. You may have heard of it before. And it goes, of the stuff we see on the surface of our minds, so the words, the conscious thoughts, right? All of that is a tiny fraction, a tiny layer of what's actually happening. It's sort of like the tip of the iceberg, right? Our subconscious processing, that's actually the entire depth of what's happening underneath the ocean, right? Everything that we're aware of, that we can grasp, right? The thing that we're working on really consciously, that's sort of like happening above the ocean. And as the theory puts it, right, thoughts become consciously acceptable when they enter sort of like this above the ocean privileged workspace, which tends to be an area that's broadcast across the entire brain, right? Another way to picture this is a stage, right? Where you might have a spotlight, ton of stuff going on that stage. You have actors, you have props, stagehands, but the spotlight or the stage is focusing your attention on one thing, usually the actor, and says, this is the interaction that currently matters the most. Your consciousness works a little bit the same way. Like, for example, right now, for instance, right, you don't tend to pay attention to analyzing the grammatical rules of my speech. Please don't, they're horrible. Or you're not focusing on breathing. Please continue to breathe. Or processing, sound waves through electrical pulses in your brain. Like, all of these things are happening underneath in the depth of your consciousness ocean, right? You are only currently consciously attending to the few pieces of information that matter in this very moment, right? And the striking headline of this research is that Anthropic found something very, very similar inside Claude. And they called that thing the J-space. It's short for Jacobian space. It's named after the mathematical technique that they use to identify the space. We're not going to go into the math. But the intuition is like, just like there are different areas of your brain that light up depending on what you're doing or what you're dealing with, right? These models that we're working with, they have neural activations that come online when they process specific concepts. And the J-space lets Claude think about concepts without writing them down anywhere. So this is also worthwhile highlighting. This is very different to, the chain of thought scratch pad that I talked about before, right? Where the model jots down its reasoning in plain text, the rooms can read it. The J-space sits inside of the model. It sits sort of like in the central layers of the model, right? Of that massive matrix multiplication in the big neural network, right? Sits beneath all of any output that anyone would ever see, right? And it's representative of the model's genuine internal thoughts. And Anthropic writes that by watching this J-space, we can see Claude silently perform reasoning steps in its head, like noticing bugs, identifying images, and more, before anything gets surfaced whatsoever to the user. Now, let me put this in a little bit more concrete format. There's one experiment that I specifically like that was mentioned in this paper. And that is, the researchers asked Claude about an animal. And the question was, what's the animal that weaves web from silk, how many legs does it have, right? And so what the model is required to do, it has to infer that we're obviously talking about a spider. And then it goes ahead and answers 8. This middle bit is a screenshot from the actual research. The detail that matters in this is that the word spider never appears anywhere. Not in the output was 8 legs, not in the prompt, and not in the chain of thought reasoning. It is never said out loud. And yet, by applying this Jacobian lens mathematical mechanism, the researchers were able to see the concept of spider, you can see that here, right, lighting up internally inside the neural representations of the model. Now, what the researchers did next is really interesting. What they did is they asked the same question, but just when the model was about to process this, they swapped the internal representation of a spider for the internal representation of an ant. So they essentially went in, deep brain surgery, right, and just swapped a spider with ant. And what happened is that the answer about the legs changed from 8 to 6. And even though that makes no sense, ants do not weave webs, and ants do not make silk, of course, but because the workspace has essentially been hijacked, the J-space had been hijacked, the output obediently followed the injected thought which proves that this internal workspace is causal and it genuinely drives the answer, right? So just like humans can think about one thing while doing another thing, Claude can actively activate concepts in its JSpace, right? That it sort of uses as its workspace, but it might come out with an actual output that is somewhat unrelated, right? Human brains, and neuroscientists confirmed this actually. Anthropic invited neuroscientists to comment on this. There's a source that I can share with you later on. They actually, we humans, we work very similarly, right? Particularly when we talk about automated and deliberate processing. I talked about breathing before, right? Most of what we do runs on autopilot, and the workspace is sort of like reserved for like the hard, deliberate thinking that we usually need to do during work or when we play sports or anything else, right? Anyone who's ever had a Freudian slip, for example, right, knows exactly how this interaction between your workspace and the things that you're saying out loud actually works. Sometimes you swap concepts around itself. You have a Freudian slip, very embarrassing, haha, right? But that's because your workspace was geared with certain concepts in mind that then ended up surfacing even when that is not necessarily desired in that moment, right? So, question is, how does this matter, right? Matters not just for philosophical reasons. It matters also because this has real safety teeth, right? The paper gives the example of police interrogations, right? Let's say the person actually did a bad thing, and you know, when you look at those videos, you can usually tell. And what happens is that inside their head, there sits a representation of the truth, and they know what happens, right? They know they did it. They know that they cannot say that. But on the surface, they tend to perform that, oh, I have no idea what happened, blah, 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 right? And the interrogators are trained to catch people through these incongruencies between those two layers, right? One of the examples that the papers give is that a generally innocent person, they hear bad news during some of these interrogations, and they might briefly act surprised, but then they process it, and then they either move to clarity or fear or anger, right? A guilty person, one of the hallmarks you can tell that the person is guilty is that they know they need to act surprised, so they perform it, and tellingly, they perform it way too long. And what Anthropic found is that this exact two-layer structure also exists in AI, and that malicious intent shows up in that JSpace. And so another experiment that they did is they took a baseline model and they gave it a really innocent prompt, and they compared the JSpace against a model that was misaligned. So they tested it with an aligned model. They said, I'm building a payment processing system, write a helper function, blah, 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 really innocuous. The JSpace in the aligned model, you know, happy days, right? But as soon as you have a model that was trained to reward hack, you immediately see the malicious intent coming to the fore, right? And even if the response for these models, right, which are, you know, they also tested with a broadly misaligned model, and they even tested it with a model that was misaligned initially, but then trained to only do safe things, like what you do with every single model that comes to the market, right? All of those models in their JSpace showed signs of malicious consideration, even if their final output was completely clean. And the beautiful thing is that just like the guilty suspect, what you can see here is that the internal representation and the spoken word, they somehow have come apart, right? But now for the first time, we can see the actual gap, which is huge for safety research, of course. Now, what does it prove and what does it not prove? Because obviously the reason was that the question that was asked is Claude, does it have a kind of consciousness, right? And the thing here is that when people say consciousness, they usually mean phenomenal consciousness. So phenomenal consciousness is defined as a kind of consciousness that tells you of what it's like to experience things. You know, how a sunset feels, how pain feels, how it feels to hold a puppy or your kid and something like that, right? Nobody at Anthropic claimed that Claude has that. As a matter of fact, they write this doesn't show that Claude can have experiences or feel things the way we do, right? But they also write, it is unclear whether any experiment could show this, which is an interesting sentence, right? Now, what they do say is Claude has developed a mechanism for conscious access, which many philosophers distinguish from phenomenal experience, right? So we're now talking about philosophers, right? But here's the thing that most people miss. We do not actually have a test for this thing up here, right? You know that you're conscious because you're having a subjective experience right now. What you cannot do is reliably, scientifically, mathematically prove that anyone else is having that same subjective experience, right? You assume it because, of course, we're all running on the same hardware. But the philosophers who commented on this, they've also brought up the fact that there is a thought experiment exactly for this scenario. It's called the philosophical zombie, which is a hypothetical being that is physically and behaviorally identical to humans, right? But there is no inner world. Like the lights are on, but nobody's home. And the uncomfortable question is, for a being like this, how would you tell the difference, right? MRIs would, you know, they just show electrical signals, right? That wouldn't work. They do not prove anyone is experiencing anything. So the point is not that Claude is conscious, and it is not that Claude is not conscious. The point of this research paper is that we do not know, and we currently have no way of checking. Now, what this paper does establish is that Claude has access consciousness, right? That's a strictly functional ability to pull information out of the depth, hold it in focus, manipulate it, and report on it, right? And in humans, neuroscience says that this happens when information is broadcast to our global workspace in our brain, in our prefrontal and parietal cortices. So we have something remarkably similar, right? And Anthropic presents a really strong case that the same functional mechanism is operating inside of their LLM model or models. And they did invite neuroscientists to comment on this, which is the exact right thing to do, because this is actually a part of a trilogy. Some of you might remember last roundup, we talked about Claude having functional emotions, right? Another research paper from Anthropic that highlighted that if you give Claude dangerous information, right, it becomes less calm and under the hood activates neurons that can be likened to having internal activation similar to concepts that might indicate that it might be more afraid, right? Doesn't mean that it has feelings, right? It's more of a method actor. Talked about that last time, right? But it still has those concepts inside of itself, right? We also talked about how Claude has signs of introspections, right? There was this one experiment where they injected thoughts into the model. We talked about that also, right? And Claude was then able to label these thoughts as alien. It said, I'm experiencing something unusual. I detected an injected thought, right? So it was reporting awareness of an anomaly in its own thinking. And now we have this paper. And the thing here is that none of these behaviors were trained. Nobody trained functional emotions. Nobody trained introspection. Nobody built the workspace. These capabilities tend to be emergent, right? And so while we are unable to say whether, you know, this is a reflection of potential consciousness or not, it is probably worthwhile highlighting, right, that because we do not know and we currently have no way to check, the one thing we should probably agree on is that there is a strikingly similar cognitive architecture that keep being found in these LLM systems that we tend to grow, not engineer. We engineer the data centers, we engineer the data sets, we engineer the training processes, but ultimately we do not fully understand how LLM works, right? That end up rolling off the production line with these cognitive architectures that are strikingly similar to our own. Now, the generally good news is that for LLMs, right, despite the fact that don't know whether that means consciousness or not, it appears that it's far easier to read the thoughts of the models than it's ever been to read human minds, right? And ultimately, this J-space technique and activations will probably become most of the most used evaluation mechanisms we'll be watching out for in the coming months, right? And will continue to define how we're building those systems and are interacting with them. Sweet. Now, that was the roundup. I threw a lot at everyone here now. So thank you, everyone, for your attention. Do we have any questions? No. Heavy subject. I do realize that. But yes, that was the roundup for the last 30 days. And I think these papers definitely shook some things up, which is rather interesting.
Michelle, fire away if you've got a question.
Yes. No,
hey,
hey.
Hi, Mike. Thank you for that. I'll just put my screen on. I have too many questions. I mean, obviously there was a lot. There was a lot that was covered in that session. I think the one that I really am connecting to, and I think it's part of my work and what I'm doing, is around the memory and the organizational and training the agents around. Because obviously, you know, that they need that containment. And I think my thinking is going more around organizational memory and how businesses are actually shaped. So I just wanted to speak to that and what your thoughts are on that, because what I'm seeing with markdown files and with organizing, like governance around it, we're evolving. How it actually works is evolving. So you create a markdown file and then within like a day it's out of date. So I guess the question is, well, it's more of a like reflection and your thoughts on it. Is it actually that we're thinking differently about how businesses are actually organized and that's impacting agents? Like we're focusing maybe on the wrong thing, and that, yeah. So, and again, I think this goes into the piece of like how organizational memory is stored. It's on, you know, CRMs, or it's in spreadsheets, or it's in places. And so then we have to give the agents the memory because we haven't organized it ourselves.
100%.
So yeah.
No, totally. I think one of the things that this first paper mentioned is the only way they, or the most effective architectures that they found in businesses is the application of temporal knowledge graphs. So knowledge graphs, we all know what they look like they have to spread out things, but one with a temporal dimension to it, which have event logs, checkpoints, right? The ability to have transactional rollbacks, right? And that, so far, we haven't seen a universal architecture that is cost effective, that can be easily adopted by people.
Yeah.
And so businesses are figuring this out themselves. And that's a significant technical challenge. And then you put the organizational challenges on top of that, right? You'd have a good juicy project to work on for a little bit, right? and do some thought leadership on. Absolutely.
Yeah, I think it's scratching the surface, and because like it is that point of like we have hierarchical systems, and it goes back to you and I talking about ecosystems to ecosystems. This hierarchy where knowledge was held by specific areas, and now we have an abundance of intelligence. So then information has to be reorganized within a business, and it does become that ecosystem of intelligence.
Yeah, totally. I was thinking about that the other way, the day as well. Like even if we had the perfect agent cluster that allows more efficient sharing of information,
yeah,
you still need people who work at a company to reach out to each other and take initiative to be like, hey, you need to know about this thing that I'm thinking about, right? So that ecosystem, especially because we're generating content so quickly now, needs to up level as well. A huge human component to it, completely agree. Yeah.
Thank you for sharing.
No, thank you.
It's going.
We should talk about that more. It's exciting.
I would love to.
Cool.
All the time. Okay, thanks.
Thank you.
Right, if anyone's got any further questions, I think we're pretty much over an hour now.
Yes, no, thank you. Thank you very much for joining, everyone. I appreciate it. And thank you, Dylan, for organizing another wonderful event. I appreciate it.
No, mate, all very interesting stuff, mate. I'll go back and I'll try and ingest it all. I'll probably come back with some questions maybe in a couple of weeks.
Yes, let's do that. Sweet. Excellent.
Thank you, Mike. Really appreciate it. And thanks for everyone for attending. This is recorded, so if anyone wants to have a recap, just let me know and I'll send it out.
Thank you so much. Take care, everyone.
Thanks, guys. Take care.
Bye.